Okay, so confidence intervals are a way for us to kind of estimate the mean for the population. So we can look at samples and we can figure out, okay, the population mean is going to fall between these two numbers. So it helps us make inferences. So let's see here. We're going to learn how to use sample statistics to make an estimate of the population parameter for the mean when the sample size is at least 30, or when the population is normally distributed and the standard deviation is known. So it's kind of the same thing as our central limit theorem from our previous unit. Okay. So that's what this is basically saying. Okay, so what we're going to use to start off for the center part of any of our confidence intervals is a point estimate. Okay, so this is a single value. Estimate for a population proportion. This is the most, this is the most unbiased point estimate of the population mean. Mu is the sample mean. X bar. Okay. So that is what we're going to be starting off finding. Well, how do you find X bar? Find the mean. Add them all up and divide by how many there are. Okay. So the validity of an estimation method is increased. The sample statistic is unbiased and has low variability. So low standard deviation, the spread is narrow. Okay. A statistics is unbiased if it does not overestimate or underestimate the population parameter. So remember our mean of our sample means, mu of X bar equals what? Mu. So therefore, X bar is an unbiased estimator of the mean. And then our standard error, sigma of X bar equals sigma divided by the square root of n of a sample mean is decreased by increasing n. So the larger the sample, the closer you are to the population standard deviation. And we talked about that last unit. So in a random sample, the length of work commute of 32 people is listed below. Find the point estimate of the population mean. Well, what's the point estimate of the population? What did we just say? Highlighted it. X bar. So you're just finding X bar. Okay, so add up those numbers and divide by 32. So when you add them all up, what do you get? Anybody else get 303? Yeah. Okay. So if we take 303 and we divide by 32, remember we're going to round one more than our data values. So we're going to do 9.5. And that's your point estimate. Okay. So from example 1, the probability that the population mean is exactly 9.5 is virtually 0. So instead of estimating mu to be exactly 9.5 using a point estimate, you can estimate that the mean lies within an interval. So our interval estimate is an interval. Or range of values. Used to estimate, bless you, a population parameter. So although you can assume that the point estimate in example 1 is not equal to the actual population mean, it's probably close to it. So to form an interval estimate, we're going to use the point estimate as the center and then add or subtract a margin of error. So we're going to assume that our margin of error is 2.3. And we just found that our point estimate, X bar, was 9.5. Okay, so we're going to take 9.5 minus that error, so 2.3. And that's going to be less than our population mean, which is going to be less than 9.5 plus 2.3. Well, it's 9.5 minus 2/10, or sorry, 2 3/10. 7.2, which is less than our mu, or our population mean. And what's 9.5 plus 2.3? 11.8. So we can say that our population mean is somewhere between 7.2 and 11.8. Okay, and we're going to talk about here in a bit how confident we are in that. Okay. Questions with the adding and subtracting to find the interval. All right, so the level of confidence. So we can find very wide intervals or very narrow intervals for the population mean. It's all based off of our confidence, which is based off of our z-scores. So the level of confidence, C, so we use a lowercase c for it, is the probability that the interval, it's actually going to be the interval estimate, contains the population parameter. So for this one, we're looking at our mean, so it'd be the population mean. Okay, and this is assuming that the estimation process is repeated. I'm assuming that the process is repeated. Okay, so from the central limit theorem, when n is greater than or equal to 30, the sampling distribution of the sample means is a normal distribution. And if the level of confidence C is the area under the standard normal curve, it's between the critical values negative Z sub C and positive Z sub C. So there's going to be subscripts of C representing whatever percent you're finding. Okay. And this picture shows this to you. So when we've been saying find the z-scores that correspond to 80% of the data in the middle, you're actually finding critical values. So that's what you're going to be doing. if you look at the bottom of table 4, okay, it shows you your 4 most common critical values. Okay, it shows you 80, it shows you 90, 95, and 99. Those are going to be the 4 most common. So if you need to, put a box around it, star it. That's what you're going to be using the most. Okay. And those are also kind of listed here on the bottom. It doesn't list 80. It shows you 90, 95, and 99. Okay. Questions with that? Okay. Okay, so the difference between the point estimate and the actual parameter value is called the margin of error. And we use a capital E to represent that. Okay, so when the mean is estimated, the sampling error is the difference between X bar minus mu. In most cases, our population mean is unknown, and X bar varies from sample to sample. However, you can calculate a maximum value for the error if you know the level of confidence in the sampling distribution, which is what we're going to be calculating here in a second. So, given a level of confidence C, the margin of error E is the greatest possible distance between that point estimate and the value of the parameter it's estimating. Okay, our formula that we use, so capital E equals Z sub C, so our critical value, times that standard error of the mean, so sigma of X bar. Okay, well, remember our standard error of the mean, we have a formula for that. So we can break this down further to be that critical value, Z sub C, times the population standard deviation divided by the square root of n. Okay. So in order to use this technique, it's assumed that the population standard deviation is known. This is rarely the case, but remember, if n is greater than or equal to 30, we can assume that it's normally distributed and use our sample standard deviation as our population standard deviation. So, using the information from example 1, where we found that X bar equals 9.5, we want to find the margin of error for a 90% confidence interval. Okay, so I'm going to leave a blank here for a second. And then let's do Z of 0.9. Those are the 3 things we need to find. Okay, so remember when you're finding, you have a list of numbers, and our standard deviation, we can just type them all in to our calculator if it's not already given to you. So I'm going to slide this up real quick. So if you want to refresh your memory on this, go to Stat Edit, and then you're going to type in all these numbers into your list for L1. Okay, and once you have that list typed in, remember you're gonna hit second quit, go to stat, go to the right for calc, and then hit enter until you get your list. Okay, so you can check, you should get a sample mean of 9.5, very first thing listed. And then we're looking at the sample. So what was our sample standard deviation? Anybody get it? 6.99. So I'm going to round that to the 1 decimal place. So let's say 7.0. And if you're having trouble finding that standard deviation using your calculator, let me know and I'll help you once we start working on homework. Okay, looking at our level of confidence. So our C is 90%. So what is the critical value from the table? And we're just going to look at the positive. 1.645. Okay. So then to calculate E, we're going to plug in what we know. So our critical value, 1.645, times our standard deviation, 7.0, divided by the square root, and our sample size was 32. And then plug that in your calculator. What'd you get? 2.0355. Yep. So we're gonna always round the margin of error to the same as our mean. So we're gonna go 1 decimal place, so 2.0. We're gonna round the same as our X bar. So 1 more than our data values. Okay, you have your formula for standard deviation, or we can use our graphing calculator. So I'm going to leave that the way it is. So now that we found point estimate and the margin of error, we can find our confidence interval for the population mean, which is just going to be a C confidence interval for the population mean mu is X bar minus E, which is less than our population mean, which is less than X bar plus E. Okay. The probability that the confidence interval contains mu is C. Okay, and then again, same round off rule as the sample mean. Okay. All right, so we're gonna go through the steps of finding that. I'm gonna kind of jump back and forth between writing it in words and writing it in symbols. So first thing we want to do is we want to verify that the standard deviation is known. The sample is random. And either population is normal. I'll move over to the next box, sorry. Or n is greater than or equal to 30. Okay, so we need to know our sigma is known, or that we can assume it based off of the sample size. And we have a random sample, and that either the population is normal or the n is greater than or equal to 30. Okay. Second thing we're going to do, and I'm going to write this over on the right, is that we're going to find our point estimate. So X bar equals the sigma of X divided by n. So the same thing we've been doing. Then we're going to find the critical value. Z sub C from table 4. Then we're going to find our margin of error E using our formula E equals Z sub C times the standard deviation divided by the square root of n. And then lastly, you're going to write your confidence interval. So X bar minus E, which is less than our population mean, which is less than X bar plus E. Okay. So if we wanted to construct our 90% confidence interval, we found that our X bar equals 9.5, and our margin of error E equals 7.0. We're simply going to subtract and add those. So we're going to do 9.5 minus 7.0 is less than mu, which is less than 9.5 plus 7.0. Okay, what's 9.5 minus 7? 2.5 is less than mu, which is less than, add them, 16.5. Okay. So the other way you can write this is you can write it in parentheses, 2.5 comma 16.5. And I'm perfectly fine with you doing it that way. The way you'll see it on your homework, like in the first couple steps, you can also write it as 9.5 plus or minus 7.0. I do not want to see this. You can add and subtract. I have faith in that, okay? But you will see that written in your homework a little. Are we good with going an extra step and adding and subtracting on our own? Cool. All right. If the population is normally distributed and the population standard deviation sigma is known, you may use the normal sampling distribution for any sample size as shown below. This is what we're going to look at tomorrow. Okay. So your homework is posted. It is 25 questions, but, and I'll look up what number it was, you only need to do before tomorrow what we've done in notes. Okay. Then we'll look at looking at an actual application problem and then going backwards to find the sample size minimum tomorrow. Okay. If you want to go through and do the whole assignment, you can. But we'll finish up notes tomorrow. Okay. All right.